Okay, so this is our optimization problem, and the question is, you want to smuggle a precious metal out of a country by disguising it as a single cylindrical barrel closed at both ends. The cost of shipping is $7 per cubic foot. Once you are out of the country, you can sell the metal $8 per square foot. Assuming that you designed the barrel with the height equal to twice the diameter, how many square feet should you smuggle, and what will your profit be, presuming you want to maximize the profit? So the first step is drawing it out. And so we know that the height is equal to twice the diameter. And so in order to make it in terms of radius, we said that the radius is equal to h, and then the height is 4 times h. So we just made it so it would be easier when we plugged it into the equation. And so we know that this is profit because it says that they sell the metals for $8 per square foot, and so that's surface area. And then the cost of shipping is $7 per cubic foot, so that's volume. And so we know from that we're going to need the volume and surface area equations, and then we're going to need to relate the two. So first we write out our volume equation and our surface area equation, and then we replace r with h and height with 4h, so that we have it all in terms of h's so that we can solve for h. Do the same thing for the surface area equation, and then we just simplify it. And so the next step is we need to relate the two. And so this is where it gets a little bit tricky, because you have to remember, well, first of all, you need to do surface area minus the volume, so that you're taking the profit minus the cost in order to get what you're going to make. And we know that profit is $8 per square foot. So you have to multiply surface area by 8 and volume by 7, because the cost is $7 per cubic foot. So you solve that and you get this, 80 pi h squared minus 28 pi h cubed. So now we need to find what h equals. And in order to find h, you need to take the derivative. So we found the derivative, so 160 pi h minus 84 pi h squared. And then you set the derivative equal to 0. And when you solve, you get h equals 40 over 21, or 1.9. So now that we know what h equals, we can plug h back into the equation we got up here in order to get our profit. So we solve that, we plug it in right here, and we get a maximized profit of $303.94. So now, in order to prove that this is a maximum, we need to do the second derivative test. So we find the second derivative of the problem, which we got is 160 pi minus 168 pi h. So now that we have the second derivative, we plug in what we have for h, 1.9, and we get that equal to negative 500.14, which is less than 0, which means it's concave down, proving that this is a maximum. Okay, so the second part of the problem asked us to find how many square feet you would need in order to maximize the profit. And so we already found h in the last part of the video, so now we just need to take h and plug it into what we already found for the surface area. So we've taken the surface area equation, as I previously explained, and plugged in h for all the variables so that our only variable is h. We know h is 1.9, so we plug h into it and we get 113.41 square feet, which would give us a maximized profit. Okay, so for our related rates problem, we have two taxi cabs beginning at the same point, and one of them is traveling north on Park Avenue and the other is traveling west on 59th Avenue. The one heading north is traveling at 40 miles per hour and the one heading west is traveling at 30. Both of the cars have the unbelievable fortune of not being stopped by traffic lights or slowed by traffic. When the taxi cab on Park Avenue has gone half a mile, how fast is the distance between the two cars increasing? So basically we know dx over dt, the rate of change of the car heading north is 40 miles per hour, the rate of change of the car traveling west, 30 miles per hour, and we knew that x, the distance that the north car had traveled, was half a mile. So what we were left with, we needed to know y, the distance the car traveling west had traveled at this point, and s, the distance between them, and the rate that s was increasing. So basically we
first we wanted to find y, this distance. So we used a ratio because we knew that both cars had left from the same point at the same time and that neither of them had been stopped by traffic or anything. So we used the ratio y over 30 equals half over 40. And then we got y equals 0.375 miles. So once we knew that, we used the Pythagorean theorem, and instead of using a, b, and c, we used x, y, and s. And we found the derivative of this so we could actually find the rate of change of the s of the distance between the two cars. So we came out with 2x times dx over dt plus 2y times dy over dt equals 2s times ds over dt. So we have all the values except for s and ds over dt. So in order to isolate ds over dt, we need to find s first. So we just use the Pythagorean theorem with s squared equals 0.5 squared plus 0.375 squared. And we got s equals plus or minus 5/8 of a mile. So this is the distance between the two cars when the car traveling north has gone half a mile and when the car traveling west has gone 0.37 miles. And because we know it's a distance, it has to be positive. So we plugged all the values back in here that we knew, and then we isolated ds over dt, again, the rate at which this is changing, the rate at which the distance between the two cars is increasing. And we got 50 miles per an hour. For our graphing problem, we were given the equation n of x equals 5x over x squared minus 2x minus 3. So the first step to solving this graphing equation was finding the domain. In order to find the domain, we factored this denominator, x squared minus 2x minus 3, and from that we got x plus 1 times x minus 3. And so the zeros of that are x equals -1 and x equals 3. The next step was then finding the asymptotes. Now for the vertical asymptotes, we could use the same zeros we found from the domain. So x equals -1 and x equals 3 again. For the horizontal asymptotes, we simply set the numerator, 5x, equal to 0, and we found x equals 0. And then the next step was finding the zeros, and again, the zero we found was x equals 0, and thus the y-intercept is at the origin 0, 0. Then for the local extrema, first we had to find the derivative, which was negative 5x squared minus 15 over x squared minus 2x minus 3 squared. So for finding the local extrema, we set the numerator equal to 0, and from that we found x equals plus or minus root -3, which doesn't exist. So then we simply put on a number line where the graph was increasing and decreasing, and we found that when x was less than -1, it was decreasing, and between -1 and 3, it was still decreasing, and after...
Okay, so next thing we had to do was find the inflection points. We already have the derivative, and we found the derivative to be negative 5x squared minus 15 over x squared minus 2x minus 15. So the next thing we needed to do was find the second derivative in order to find inflection points and then concavity. So we found the second derivative by using the quotient rule, and there was a lot of algebra in between these 2 points, but in the end you end up with 10 times x cubed plus 9x minus 6 over x squared minus 2x minus 3 cubed. So in order to find the zeros of this, we graphed and saw that there was a zero at 0.63. So that is the inflection point of the original function. We put this on a line in order to find concavity. We have our asymptotes -1 and 3 on the line, and then we have our inflection point of 0.63. We plugged in numbers before and after each of these points into the second derivative to see if they were negative or positive. If they were negative, we had concave down, and if they were positive, concave, positive, concave up, negative, concave down. And so that is our concavity. Then we graphed the function. So we have the asymptotes at -1 and 3. There's also an asymptote, a horizontal asymptote at 0. We have the concave down from -infinity to -1, concave up from -1 to our point of inflection at 0.63, concave down again from 0.63 to 3, and concave up from 3 to infinity.